Okay. I think maybe we might begin, given that we have quite a tight schedule. So hello everyone, welcome. Together with my co-chair Jay Bhagwan for the Water Research Commission, we'd like to welcome you to today's session on valuing wastewater for new solutions. So you will see from the program, and I think we should have the slide there. This is a high-level strategic session that will give a perspective on the changing value of wastewater and sludge and circular pathways that can be chosen to produce a resource that can bring a value-based offer. We'll have two keynotes today. Dr. Josef Landsteiner, who is Technological Director and R&D Research Director for Warburg in Austria, who will give us a high-level introduction and will tell us more on what is happening on the reuse front and the associated benefits and issues of concern. And we also have a second keynote who is Kartik Chandran, who is Professor of Earth and Environmental Engineering at Columbia University, who will highlight the pathways and circular economy and value proposition of wastewater and sludges. So we will start with the presentation of Dr. Josef Landsteiner. I will pass over to you, Josef, to put up your presentation. And we will leave the questions to the end. If we have time, we can do it straight after the presentation. And I would just like to ask you to put your question in the chat line. That would be wonderful. And then I'll go through the chat line after the presentations. Josef, yep.
Can you see my
Yes, we can.
presentation?
Thank you, Josef.
Yes.
Over to you.
Thank you, Stephanie. First, the outline. I will give you a short introduction. Then I will talk about potable reuse, urban and industrial reuse and recycling, and then I will draw some conclusions. The major drivers for water reuse and recycling are, first of all, water shortage caused by climate change, population growth, urbanization, and industrialization in developing and emerging economies. There are, of course, economic reasons. Used water or wastewater is a drought-proof resource. There's a lower freshwater demand, reduced wastewater discharge fees, and resource recovery is an option. Very important. There is a boost in water supply security, and last but not least, policies, regulations, and guidelines. For example, the treated wastewater reuse policy of the Indian state of Tamil Nadu, issued in 2019. Now, I will come to potable reuse. The major indirect potable reuse projects are in this slide. I would say Orange County and Singapore are the most prominent ones. In Orange County was a pioneer, starting with the Water Factory 21 in 1976. And the groundwater replenishment system was started up in 2008, and the extension, it was extended in 2015. There will be a video later in this session. Singapore, New Water, they have meanwhile 5 new water facilities, and 2 more are intended to build. San Diego, Pure Water San Diego project is a huge project, and they will build 2 pure water facilities. IPR is also a topic in Chennai, India. Pilot testing in a 10 MLT scale will be started in a few months. In India, IPR is also a topic in the megacities of Chennai and Bangalore, for example. The Singapore IPR scheme, new water is blended, but only during dry periods, with other sources, rainwater, raw water imported from Malaysia in a reservoir, the environmental buffer. The blended raw water is treated in a conventional waterworks and distributed to the population. The sewage or used water is treated in a sewage treatment plant. They call it water reclamation plant. The secondary effluent, the water is reclaimed in the new water facility. Most of the water goes to industries, and as mentioned, only a small part is used for IPR. They use an RO process, therefore the RO concentrate has to be disposed. This is the reverse osmosis process unit at Changi Sembcorp at the plant, and the capacity is 228,000 cubic meters a day. A new water storage tank at Bedok. The branding is excellent in Singapore, and you can see this here in the visitor center. The kids are educated, and we have to start with the youngest, make every drop count. So they have a very good education policy also. And now I come to a hybrid project. It's IPR and DPR. During regular rainfall, the reclaimed water is blended in an environmental buffer in the Gaborone Dam during droughts. The empty, silty environmental buffer is bypassed, and then DPR is practiced. The project is in the tendering stage. It can be expected that the contract will be awarded in September or October. The initial phase capacity is 25,000 cubic meters a day. Finally, it will be extended to 50,000 cubic meters a day. And they use a non-RO multi-barrier system. The scheme of this hybrid system: sewage treated in the Glen Valley used water treatment plant or sewage treatment plant, polished in these ponds, then treated in an advanced water reclamation process. As mentioned, during droughts, the environmental buffer is bypassed. Then we have DPR, and the water from the dam water, the blended dam water, is during IPR and also DPR is treated additionally in a conventional treatment plant, the Gaborone water treatment plant. After disinfection, the water is distributed to the drinking water network. Now, DPR projects. Windhoek, Namibia, started up already in '68, the old Goreangab water reclamation plant, which was operated until 2002. In 2002, the new Goreangab water reclamation plant was started up and has been successfully operated, meanwhile, for 20 years. Another DPR project in Southern Africa is Beaufort West, a smaller one started up in 2011. Big Spring in Texas, blending operations started in 2013. In Wichita Falls, there was an emergency operation for 1 year. After sufficient rainfall, they switched to IPR. And El Paso, also in Texas, this project is in the tendering stage of the sewage treatment plant. The sewage treatment plant will be extended by disc filters and UV in order to get a high quality water, secondary effluent or a tertiary effluent for this advanced water purification facility, which is in a 90% design stage. Now to Windhoek, a simplified direct potable reuse scheme. Sewage is treated in this Gammam's wastewater treatment plant. The secondary effluent is polished in maturation ponds and then reclaimed in this advanced multiple barrier system, the new Goreangab water reclamation plant. The The reclaimed water is blended with groundwater and treated dam water. In Windhoek, also groundwater recharge is practice. Bernice will present this practice later in this session. Groundwater is recharged with reclaimed water and treated dam water, and industrial wastewater is strictly separated. The project structure, financing has been done by European Investment Bank, German Development Bank, Kreditanstalt für Wiederaufbau, Municipality of Windhoek. The plant, the facility was built by DB Thermal and Wabag and is operated by the Windhoek Goriangap Operating Company. Shareholders are Veolia Water and Wabag. The new Goriangap water reclamation plant, you can see the different treatment stages: pre-ozonation, coagulation, dissolved air flotation, dual media filtration, ozonation, biological activated carbon filtration, granular activated carbon filtration, ultrafiltration. Is also disinfection and pumping station. And there's an R&D building. There is continuous R&D in order to continuously improve the process. Acceptance of direct potable use, major reasons. Or the major reason is, since the beginning of direct potable use in '68, no outbreak of waterborne disease has been experienced and no negative health effects have been attributed to the use of reclaimed water. So the Windhoek case and all the other potable reuse case show that this potable reuse is a safe water management option. Now, urban water reuse for irrigation. Madinati is a satellite town of Cairo. A lot of green areas. The irrigation water demand is high. The water is reclaimed by a conventional system, activated sludge with sand filtration and disinfection. This disinfected water is pumped to the irrigation network. Capacity 2 times 40,000 cubic meters a day. Here you can see the aeration tanks, pumping station, reclaimed water standards comparable to the EU regulation Class A water. Now, industrial water recycling and reuse. First case, Dangote Refinery and Petrochemical Complex, Nigeria. Nigeria is the most populous country in Africa, more than 200 million people, largest economy in Africa. The Dangote Refinery and Petrochemical Complex will be started up at the end of this year. Water management is done by raw water treatment, raw water from a lagoon, effluent treatment, and water reclamation. This slide shows the reclamation system. Here, 4 different streams. This is the oily water stream, core technology, ultrafiltration, reverse osmosis, and mixed bed ion exchanger. The reclaimed water is reused in the boiler of the refinery and petrochemical complex. This slide shows, this photo shows the installation of the reverse osmosis process unit during the pandemic. Capacity 32,000 cubic meters of RO permeate. Next case, Coimbatore water reclamation project in Chennai, India. Capacity 45,000 cubic meters a day, was started up in 2019 after the severe drought in Chennai, using an advanced multiple barrier system, reclaimed water supply network, 68 kilometers, and the water is reused mainly in different industries, mainly in the automotive industry. Chennai, at the Gulf of Bengal, the water reclamation plant in the southwest of Chennai. This is the industrial corridor between Chennai and Bangalore, and the water is supplied to this industrial area. And the aim is industrial reuse to boost the overall water supply security. A lot of water, of fresh water in these reservoirs and lakes is saved for potable purposes. Simplified process flow diagram as in Dangote, core technology, ultrafiltration, reverse osmosis. And the water is in this case disinfected with ozone and then distributed to various industries. Reverse osmosis unit with Dow membranes. And here you can see the beneficiaries of the reclaimed water. Automotive industry, that means Hyundai, Nissan, Yamaha, Royal Enfield, and other companies. In Chennai, there will be organized the 13th IWA International Conference on Water Reclamation and Reuse from 15 to 19 January next year. So I would like to cordially invite you to attend this very exciting conference. Conclusions. Large quantities of fresh water can be saved by water reuse and recycling. This boosts the water supply reliability or security, which can be endangered by water stress. And the environmental impact is reduced by water reclamation and reuse. And in many cases, water reuse is cheaper than other options, such as transport from distant sources. The undisturbed functioning of the water supply, especially during a crisis, is essential. This can be guaranteed by properly designed, robust, resilient, and redundant multi-barrier processes, and professionals own them. Finally, it can be concluded that water reuse and recycling represent essential elements for a circular economy and for sustainable development, environmentally, economically, and socially. I thank you for your attention.
Thank you, Josef. Perfect timing, and thank you for giving us a global overview of water reuse case studies. We have some time for questions. We have about 2 minutes before the next presentation. If you have any questions, you can put it in the chat line. In the meantime, Josef, I was going to ask you, how are those water reuse projects financed? You know, especially you mentioned projects in Chennai, Botswana. How do they get financed?
Yes. The Chennai Coimbatore project has been financed by the Indian government's AMRUT project. That's the Atal Mission for Rejuvenation and Urban Transformation, and also by the state of Tamil Nadu with the investment promotion program. And the client, this is Chennai Metropolitan Water Supply and Sewerage Board, is selling the water to a company. It's called SIPCOT. It's Small Industries Promotion Corporation of Tamil Nadu. And this SIPCOT sells for 65 Indian rupees. That's approximately 80 euro cent. So Chennai Metro gets 80 euro cents for the water, and SIPCOT sells the water to these various industries for 1 euro per cubic meter. So water has a value in water stressed Chennai. And in Gaborone, the water is financed by the World Bank subsidiary IFC, International Finance Corporation. It's a 25-year DFBOT project. That's design, finance, build, operate, transfer project. That means a PPP project. And the client in Gaborone gets a loan from IFC. It's Water Utility Corporation.
Oh, okay. Thank you
of
very much
Gaborone.
for that information, Josef. It's great. Thank you. I think I can't see any questions in the chat line, so we'll pass over to the next presentation. Thank you, Josef. We will share the next presentation by Professor Kartik Chandran, who's Professor of Earth and Environmental Engineering at Columbia University. Professor Chandran will highlight the pathways and circular economy and value proposition of wastewater and sludges. And his presentation is entitled Demystifying the Reuse of Circular Economy, the Future. Josef, you need to undo your presentation so that Kartik can.
Okay.
Thank you so much. So I pass over to you, Kartik.
All right. Can you see my screen?
Yes, it's coming. Yes, you just have to open up the first slide. Wonderful. Thank you so much. I'll pass over to you, Kartik.
Thank you, Stephanie, and thank you to the conveners of this session as well. So I'm going to again go beyond water, which I think makes for a nice sequence here after Josef's presentation. And so here we are going to be looking at what the other constituents are of the different waste streams, not just sewage, not just fecal sludge, but also the solids which have to be addressed. And so if you just take a step back, perhaps some of you have seen some similar schematics. If you take a step back and take a look at the overall water cycle, we are essentially starting here with clean or pure water, and then we basically use it for different objectives. And this is what we produce. The bottom line is, when we talk about streams like sewage or wastewater or other waste streams or waste-related streams, I think one of the key things to keep in mind is that even though there is a very negative connotation associated with these streams, there is actually something positive that we are adding to these streams in terms of carbon, nitrogen, phosphorus, and so on and so forth. And so that is what I'm going to focus on. Alternate approaches, end products, and just another way of thinking to avoid sinking in even more resources, more energy, more money into these water plus X streams, rather using the water plus X, taking the X out, and then perhaps fostering other activities. And so that's one. This is again when there are questions, we can answer them. So I'm going to keep this fairly quick and fairly high level. So we see that in terms of the model for water today, and on the other hand, we also see models like this or factoids like this that essentially highlight that almost universally access to limitation in terms of the access to wastewater treatment around the world. But the bottom line again here is there is a limitation in terms of access, even in some of the most developed countries in the world. And so why is that the case? If we take a look at, let's say, a process configuration for conventional wastewater treatment, all of this works fine, or all of this works to differing extents in different parts of the world. But universally, again, almost universally, one of the major limitations that is linked to the limitation in terms of access is limitation in terms of other resources that we need to sink in to run these wastewater treatment technologies. Wastewater treatment and reuse. One of the biggest resource limitations is associated with the lack of energy or limitation of energy in many of the countries again, this is nearly universal, even in the so-called first world and other parts of the world as well. So what do we do then? We just cannot relentlessly, mindlessly keep putting the same technologies in these places and then hoping or praying that these would work. We have to change the framework. We have to change the axis, and that's what I'm going to focus on. And so, yes, water reuse is good. Let's start to take a look at what else is inside these water plus X or so-called waste streams. What else is inside? What else can be recovered? When we talk about, let's say, the liquid stream and the solid stream, there are different endpoints, different value propositions. So when we take a look at the liquid stream, there's always the opportunity to extract chemicals, extract energy. And I don't mean to say that this is going to cure everything. This is applicable everywhere. No, that would be just another mistake in the making. What I'd like to suggest rather is that take a look at your own systems, figure out what needs to be recovered. Perhaps water is one product in some parts of the world. Maybe it's not in other parts of the world. Maybe some of these end products are. So what are we talking about here? Energy for sure, but then in many other contexts, chemicals could be something to be could be end products that can be recovered and used within the boundary of treatment to foster treatment. And so chemicals, energy on the liquid side. When we talk about biological reactors, as is the case for most of the treatment processes, again, we are talking about end products in terms of chemicals and energy. And I'll get to what these chemicals are in just a few minutes. And then when we talk about the sludge, this is where we are talking about concentrated streams, which basically means our reactors, our processes can be much, much smaller in size for the same volumetric load. And so there's, again, we are talking about energy and chemicals. And what have we not talked about here? We have stopped talking about wastewater treatment. It's now going towards recovering resources, chemicals, energy, and more from these systems, perhaps from the same treatment processes now which have been reoriented towards recovery rather than removal. Now, the main questions still remain. Does recovery even make sense? I'm not going to be able, no one's going to be able to provide a generalized answer. We have to go in and take a look at our specific systems. So what is there? Let's start with at least trying to recognize what there is, how much there is. So essentially the well-known culprits are carbon, nitrogen, and phosphorus. So if we take a look at how much nitrogen we discharge compared to how much nitrogen we need, yes, human waste can offset a fraction. Phosphorus in human waste can offset a fraction of the demand. But the biggest bang for the buck, I think, lies in the organic carbon, because carbon gives us a lot more flexibility in terms of what we can process and what we can produce. And that's really the highlight here. We need to start looking at carbon. It's not as if we have not looked at carbon. We've yielded to temptation and pretty much go all the way to methane. That's something that needs to change as well. So next question is there a business case? And again, I'm sure all of you have seen schematics like this. This number here, the 50 billion figure in terms of the global demand for water and sanitation services is a gross underestimate, but at least there is something, there's a reference, but again, this is a gross underestimate. And again, we've talked about India. India also, there are some impacts in terms of lack of sanitation. These impacts are not just restricted to India, they are just universal as well. But the bottom line again is lack of water and sanitation impacts productivity in terms of GDP as well. And then there are other figures as well in terms of populations that lack water and sanitation. There are other benefits as well in terms of getting to advanced levels of recovery and or reuse. The moment we start talking about carbon, nitrogen, phosphorus recovery and or removal, we are directly going to be reducing the uncontrolled emission of greenhouse gases such as nitrous oxide. So treatment, and we can come back to this during the Q&A if there's any interest. So the IPCC also in their latest report took some values from our study in 2010. The report came out in 2019, and there again there's a direct link in terms of the degree of treatment, recovery and or reuse or removal, and the production and emission of greenhouse gases as well. Okay, so what can we do? So yes, I think it's fairly convincing that we need to do this. What can we do? What is there? So when we talk about human waste, this is what we are talking about. Majority of the waste is water. That's what we're made of. That's what we discharge. And then there are some other materials. Again, in the fecal matter, it's primarily carbon, organic carbon, and all the pathogens. And the urine streams contain the nitrogen and phosphorus and some unbiodegradable carbon. And so we can basically go step by step. We can go fraction by fraction and then decide what we need to make where in the world. And that's the kind of framework that we need when trying to figure out what to make, what to recover, where to do this. Okay. And then if we can develop technologies which are really agnostic to the waste stream, waste in quotes, because these are not really wastes, that'll be good as well. What can we do? This is just, I don't want you to sit and read each and every box here. The point is these technologies relating to recovery of carbon need to be flexible. So I'm pointing to certain technologies that are really, really flexible in terms of what they can take in, what they can produce. And you can see and we are not even scratching the surface here. This is what our community, our industry is actually capable of with the waste streams that we are dealing with. All of this is possible if we stop thinking and doing just methane production. This is everything else that we can do. And these chemicals are much, much higher value, especially outside the boundary of treatment compared to biogas and methane. And so what is it that we are trying to do from a more technological perspective? I'm just going to fly through this. All we are trying to do is, if you consider this oval as a microbe, as a microorganism, essentially what we are trying to do is play with different, giving it different substrates on the left-hand side, giving it co-substrates, and then coaxing or encouraging these biological processes to make newer things, not just methane, newer things, more useful products, basically. Okay, scale becomes very important. So one question could be, are we going to do this at full scale in a centralized treatment process? Maybe. There is also, on the other hand, there's also a very high degree of attraction in terms of scaling down such recovery processes. Right? It's not a volumetric scale down. It is essentially stopping the dilution of human waste with all other non-human waste streams that allows us to make these systems much more efficient and much more productive. So issue of scale also needs to come into the conversation, into the designs as well. And then with scale, we can fit these systems into different environments, into different communities, in which case nitrogen and phosphorus come into the picture now, and then there's a link to food production as well. So finally, I would say, just to round all of this off, that the potential is there. The potential is actually quite immense. There are technologies coming up. There are processes in place right now as well in some parts of the world. There's immense interest. However, we should not shift our mindset completely. So so that we are competing with, let's say, fuel production or chemical production or plastic production and so on and so forth, materials production. We need to do all of this to sustain and support a different objective, which in our case is providing higher degree of access to water and sanitation. So that's, in my view, the higher objective. If we can make fuels from fecal sludge to run a fecal sludge treatment process, that to me is much more attractive rather than sitting in the middle of nowhere just making a chemical that no one's going to use. So that's all I have. Thank you again for having me as part of this session.
Thank you very much, Kartik, for your presentation and giving us a good overview of the resource recovery potential. We've got some time for 1 or 2 questions. If you can use your chat line to ask the questions. Maybe I can start with a question about the scale of implementation of those resource recovery options. I mean, when does the scale become cost effective?
Yes, so again, there is not a single answer, right? It really depends on, it's almost like an optimization process here. So one of the decisions to be made in many cases is what to recover. So if you're starting to talk beyond biogas, beyond methane, then there needs to be a connection to some industry, let's say, that can use the products. I'm going to take a very, very simple example. Let's say we are talking about anaerobic fermentation of sludge to produce what precursors of biogas, precursors of methane. So these are volatile fatty acids. This is what happens when a digester goes sour. We think about this as a negative product, but in fact, it's not. These products, these chemicals, these fatty acids can actually be used within the boundary of a treatment plant to remove nitrogen and phosphorus, or even recover phosphorus for that matter. So in this case, the scale could be almost seamlessly within the treatment process. So imagine all the sludge that comes into a centralized treatment plant, but instead of that sludge being dumped or converted into something that's not easily used, it's being converted into something, fatty acids that can be used within the boundary of the system. So this can happen at a large scale. On the building scale, we can talk about recovering nitrogen and phosphorus, but again, not in isolation, but towards supporting, let's say, urban agriculture in communities. And in most cases, cities have been called food deserts. This is something that this is an approach that we can use to offset, to move away from this model again. And this is also happening in many cities around the world, where abandoned communities, abandoned neighborhoods are being now revitalized based on the foundation of urban agriculture and more, but at least urban agriculture.
Right, wonderful. Thank you very much, Kartik. We have question from Joan. Can you speak more to the treatment and recovery of resources of animal waste?
Yeah. So Joan, thank you. One of the first projects I actually worked on thinking about beyond methane was in Ghana. Animal waste, and I'll come back to why I bring this in. Animal waste is actually different wastes they all have carbon, nitrogen, phosphorus. The ratios might be slightly different, and so that will also drive what we do and what we recover. And so if your question is along the lines of what to do with the different composition, maybe I can go along that direction then. Yeah, so the nitrogen content is sometimes a concern when we are talking about nitrogen removal, the context of, let's say, in the US at least, let's say SPDs or NPDES permits. Why don't we turn it around? And there's a very specific hierarchy to recovery as well. There has to be a hierarchy, otherwise we're going to end up just feeding the wrong electrons in the wrong reactor and nothing's going to get recovered. And so with animal waste specifically, and even more so with animal waste, with that unique combination of carbon and nitrogen and not as much phosphorus, is that carbon needs to get taken out anaerobically, so as not to oxidize the nitrogen, the total Keldal nitrogen and ammonia. So then it's almost tailor-made for the recovery of the high load that comes in of nitrogen and or phosphorus as well. And if we don't need to recover nitrogen, we can still, since we have saved money or saved energy on the front end with respect to carbon, we can still, let's say, focus on autotrophic processes for nitrogen removal if removal is needed. For instance, anaerobic ammonia oxidation and so on and so forth, which take less energy, but then also don't utilize any organic carbon because these are autotrophic processes.
Great, thank you, Kartik. Thank you so much. We'll move on to the next part of our session, which will be 3 short video clips on aquifer recharge. And we'll have 3 case studies: California, Spain, and Kenya. And Olivier will put up the videos. So there will be short videos. And we also have 2 of the video presenters with us today if you have any questions. We have Enrique Fernandez Escalante from the Traxa Group in Spain, and we also have Carrie James from Sanitation in Kenya. So Olivier, I'll pass over to you to start the videos.
Good afternoon, ladies and gentlemen. This is Enrique Fernandez, and I'd like to expose you the results of the EARSAT project about the effect of the irrigation with reclaimed water on plants, soils, and aquifers in the Maith area. The site has been the Balearic areas, where 14 sites use reclaimed water for irrigation. 5 of them has been selected, and 11 parameters have been analyzed during 5 years for 11 different crops. The methodology was to track the evolution of 5 different parameters, and the results were positive for 10 out of the 11 crops analyzed. Regarding the soils, the methodology was also to track the evolution of 3 different parameters, concluding that no affection after a sufficient washing dose was detected in the soils of the 5 sites. And regarding the aquifers, the console model was used to compare the results for the 5 years of monitoring, and from the model, different parameters were tracked, such as nitrates, DOD, etc. And the results was the system began to work in a steady state from the 5th year. In conclusion, no one important environmental impact has been detected neither in plants nor in soils or aquifers, and the SATMAR in Maith areas entails a safe reuse, a higher water security, and circular economy, at least for the given circumstances. To broaden this information, there are 2 publications of this project on the internet. Thank you very much for your kind attention.
Welcome to Orange County, home of the Orange County Water District, a world-renowned leader in groundwater management and water reuse. Orange County Water District manages a large groundwater basin in North and Central Orange County. We are very lucky to have this basin because it provides approximately 77% of the water to 2.5 million people in our service area. 19 local water suppliers pump water from the basin and supply it directly to their customers, providing a safe, reliable, and low-cost water supply. Our mission at OCWD is to manage and protect this basin so that it can continue to be the main source of water for these agencies both now and for future generations. There are several sources of water we use to recharge the basin: Santa Ana River flows, natural rainfall, stormwater, untreated imported water from Northern California and the Colorado River, and recycled water. In recent years, recycled water has grown in importance as a source of our supply and now makes up more than 30% of recharge to the basin every year. In 2008, OCWD, in partnership with the Orange County Sanitation District, constructed the groundwater replenishment system. Orange County Water District takes the Sanitation District's reclaimable wastewater and purifies it to near distilled quality, using a 3-step advanced purification process consisting of microfiltration, reverse osmosis, and ultraviolet light with hydrogen peroxide. We are the largest indirect potable reuse facility in the world. Groundwater replenishment system produces 100 million gallons of water. Approximately 80 million gallons of the groundwater replenishment system water is pumped through a 13-mile pipeline to our recharge facilities in Anaheim. The remaining water, approximately 20 million gallons, is injected into a seawater barrier about 4 miles inland from the coast to help prevent seawater intrusion. The groundwater replenishment system has been in operation since 2008. Currently, we're constructing the final expansion of the project, which will bring total daily production to 130 million gallons by the year 2023. This will provide enough water for 1 million people and will result in treatment of all the reclaimable water available to the Orange County Sanitation District. North and Central Orange County's future depends on reliable water supplies. The groundwater replenishment system provides our region with water it can count on and serves as a model project for other regions throughout the United States and the world that are or will be facing natural and man-made water supply challenges.
So at Synergy, we view ourselves as the solution for cities. What I mean by that is cities have a massive problem with both sanitation and organic waste. So around the world, cities generate about 1 billion tons of sanitation and organic waste every year. And what we've realized is that majority of that waste actually doesn't get treated. The majority of that waste is just dumped in the environment. So at Synergy, we exist to solve that problem, where we employ a circular economy approach to collect both sanitation and organic waste from cities. Then what we do is we turn that into useful end products. So we receive sanitation and organic waste. And then what we do is we have a team of engineers and scientists who have created proprietary recipes that we feed to insects. The insects are called black soldier flies. The black soldier flies eat, they grow, we harvest, we clean, we pasteurize, and then we dry and package the black soldier fly larvae to be sold as insect-based protein. And then what happens is the flies leave residue. So the residue is then taken and it's converted into organic fertilizer. That residue is mixed with agricultural waste, and then it's taken through what we call thermophilic composting. The organic fertilizer that we produce is called Evergrow, that is sold to more than 15 counties across Kenya. And farmers who use Evergrow, especially in horticulture, are seeing more than 30% increase in yield. Beyond that, also some of the residue is taken to create biomass briquettes, where we compress at high temperature and high pressure to create briquettes that would otherwise be used for industrial boilers and other industrial heating applications. In terms of the economy, first and foremost, in terms of job creation, we have over 100 people working with us here at Synergy in terms of direct jobs created. And then if you look into our value chain, especially on the sanitation side and also the organic waste side, we have upwards of 2,000 people who, in one way or another, benefit from the value that you're creating, whether it's on the agricultural side or whether it's on the sanitation side. So it's a very beautiful story about solving problems on the sanitation or waste management side, then using circularity to solve problems in agriculture in terms of animal health from the insect-based protein perspective to feed our animals, in terms of soil fertility, which is organic fertilizer. We have the goal of, in the next 5 years, accessing more than 1 million tons of waste per year. In the next 5 years, we look to extend into Kenya, into other cities, the likes of Kisumu, Mombasa, Kilifi, then beyond that into Africa, and then moving into Southeast Asia as well. Because this is not just a Nairobi problem. I think we're talking about beyond Nairobi.
Great. So that's the end of the 3 videos. Are there any questions? We have Enrique and Carrie from Synergy with us today. So any questions for Enrique or Carrie, or you can use the chat line. Oh, I've learned something new. I've never heard about the black soldier fly before, Carrie. That was a very interesting one.
Oh, the most fantastic insect in the world. I deeply love it. And every time I see that video, it reminds me, I get excited all over again.
I can imagine.
Yeah.
Wonderful. Okay. Oh, here we go. Joan has a question for Carrie. How long does it take to get these operations up and running?
Really good question, Joan, and entirely depends on the scale of waste that we are looking to treat. The video that you saw there, that factory is taking in 200 tons of mixed organic waste a day. And if it weren't for COVID falling smack bang in the middle of construction, it would have taken around 12 months to go from construction start to ready to start operations. However, the solution that we have, because it covers a number of different waste reuse processes, we can set up a smaller scale composting to fertilizer type solution really quickly. So, you know, to process up to around 20 tons a day of compost or waste into compost, could have that up and running within 2 months. So really they give you your boundaries of minimum sort of waste tonnage and maximum timeline to get up and running.
Okay, great. Very interesting. Thank you, Carrie. Oh, and Joan, you have a question for Enrique as well. Enrique, how do you characterize the aquifer to be sure this process will be appropriate? Oh, Enrique, we can't hear you. Oh, no, we still can't hear you. Must be your...
Now?
You want... Oh, yes, now we can hear you.
Okay, I have changed the USB plug. Yes, we made an initial characterization of the aquifer before any process took place. After that, we were monitoring the aquifer quarterly during 5 years, so we could trace all the evolution of 18 different parameters. And finally, we compared the result of the model with the result of the monitoring, and the convergence was very high. I don't know if this is enough to reply to John.
Yes, yes, she's happy.
Okay, thank
All
you.
good. Wonderful.
And,
We did have one question about Orange County from Jay. Why not direct reuse? But I don't have Megan Plumley from California Orange County with us today, so I think I can't really respond to that one today. Jay, sorry about this. Anyway, I think we need to move to our next and last presentation of this session. by Berenice Naitwa from Namibia, from the Windhoek Goreang Gap Operating Company. And Berenice will talk about wastewater reuse solution to implementing managed aquifer recharge in Windhoek. So I'll pass over to you, Berenice, if you want to share your slides.
Yes,
Yes,
thank
they're
you
coming up.
so much, Stephanie.
They're coming.
Okay. I hope everybody can see my screen. So I just...
Now it's coming. Yes, perfect.
Okay. No, thank you everybody for joining us today. I want to present to you the wastewater reuse, which was a solution for the city of Windhoek in order to manage the aquifer recharge scheme. So today I will speak briefly about Namibia and its capital, why reuse, and then again, why aquifer recharge, the current water supply, and then wastewater reuse. We'll quickly look at the scheme, and then finally look at the managed aquifer recharge scheme here at the city of Windhoek. Yes, so Namibia and its capital. Namibia is a very dry country, very arid. Its capital is squashed between two deserts, the Namib Desert and the Kalahari Desert. The average rainfall in Namibia is about 360 millimeters per year. The average evaporation rate is about 2,170 millimeters per year. The city of Windhoek has a population of about 400 inhabitants, and the surface and the water supply to the city is about 70 to 75% surface water during good rainy seasons, 25% reuse, and less than 5% groundwater. The blend changes depending on whether the city receives enough rainfall or if we're going through drought periods. And the last drought was the worst in 90 years, and that was in 2000 and between 2017 to 2018, ending in 2018, where we had record rainfall. So the current water supply to the city. As I said before, we have a 3-dam system, Omatako, Von Bach, and Swakoppoort Dam. The first of these dams came online in 1968. During this period, there was a lot of infrastructure development because the city had run out of water. So traditionally, during the city settlement, the city was supplied through the underground water, and the boreholes had been over abstracted and the city ran out of water. So Von Bach was brought online in 1968, and the first reclamation plant was also brought online in 1968 to supply the city residents with direct potable reuse water. Currently, the system is operated by the National Water Corporation, NamWater, which treats the water and then supplies it to the city of Windhoek for the population. The second source for the city of Windhoek is the new Goreang reclamation plant, which was brought online in 2002, and it supplies 21 megaliters per day of water. This process was designed to treat secondary effluent from the wastewater treatment plant to drinking water quality to directly supply the city of Windhoek's residents. Because it is DPR and not IPR, it abides by a high standard of water quality parameters. And this is privately operated by Windhoek in the city of Windhoek. And then the third supply is the underground water supply. This has been since the original settlement of the city of Windhoek. This was the main water supply, and after over abstraction, when the wells had run dry, the city then changed this, brought on other supply streams online, and then this became a strategic and emergency water reserve. And this is operated by the city of Windhoek. So just a quick look at the water reuse scheme, which was spoken about by Dr. Langsteiner, a previous speaker. We have the new Gorenga water reclamation process, which is the DPR water plant in the city of Windhoek. Basically, they traditionally was designed to have two raw water sources, which is the Gamams Water Care Works and the Gorenga Dam. The Gorenga Dam has been since 2008 been offline. After which we have raw water blending, coagulation, dissolved air flotation, rapid gravity sand filtration, ozonation, which is the main disinfectant step in the process, biologically activated carbon filtration, followed by granular activated carbon filtration, and then ultrafiltration as a polisher step. The process is based upon the multi-barrier principle, which is designed to have more than one process unit to remove any pollutants in the water. Then the final barrier is that the blended water stream in the distribution should not be more than a third reuse water. So in case anything happened, there should be some dilution in the distribution process itself. This process produces a high quality water supply to the city. And this, when water quality issues were experienced during recharge of the aquifer scheme, it was then decided to use a blend of both reuse and surface water supply to the Windhoek managed aquifer recharge scheme. So the reuse source of water that already existed in the Windhoek city made it possible for recharge to actually take place in the city of Windhoek. So I'd like to speak a little bit more about the Windhoek managed aquifer recharge scheme and how it came about. So the aquifer itself had been studied since the 1950s, and because it was the main source of water for the city of Windhoek. It is a predominantly confined aquifer, which is characterized by faulted and fractured clean or you could say pure and impure quartzite, as well as schist. But the majority of the area in which injection or re-injection is done is mainly in the quartzite section of the aquifer itself. There are about 49 boreholes which are currently in place, 9 of which are for injection. The injection boreholes are separate from the abstraction boreholes in the Windhoek Aquifer Recharge Scheme. The different boreholes have different temperature ranges, where some of them are very hot. You can find them at about 90 degrees, and some of them are a normal temperature, 25 degrees. The storage capacity of the injection boreholes is about 28 million cubes, but they range between about 25 to about 60 million cubes. But in the area which the city of Windhoek is actually targeted for the injection, the storage capacity there is about 28 million cubes. The capital invested so far is about 26 million US dollars, and this was funded through the local government, the city of Windhoek itself, as well as the national government, and part of it, about 4 million, will be funded by the National Water Corporation to realize the scheme. So just a few points. Currently, the installed injection capacity of the aquifer scheme is about 3.75 million cubes per year. The abstraction capacity is 16 million cubes per year. The natural recharge, as you can see, is very much lower. So when you have years of drought, as we had during the 2006-2007 period, again, the 2012-2013 period, and then the third drought that we've had in this decade, which was the 2015-2017 period, you could see that the natural recharge with abstraction wouldn't be sufficient to actually keep the
1.1, 2.8, 3.9 plus 2.4.
Go ahead, Berenice, someone was on the line.
Oh, sorry. The natural recharge wouldn't be enough to actually keep the aquifer scheme online. The estimated losses, because it is an underground buffer, is about 3%, which is very low compared to the evaporation rates that are experienced in
14.3.
So the aim of the aquifer recharge scheme was basically for the city to utilize the maximum aquifer storage capacity to keep the water, as well as to minimize the evaporation losses for the already existing capacity that they did have for surface water, to increase water security and climate resilience for the city of Windhoek during the multitude of droughts that they have experienced in the last 20 years. And at completion, the abstraction capacity is targeted to be about 19 million cubes per year, and the recharge capacity to be about 12 million cubes per year. So very important and a key contentious point was the injectant quality. Originally, the scheme was targeting surface water, to bank surface water during times of good rainfall, and then have 100% injectant to be surface drinking water. But unfortunately, the quality of the surface drinking water wasn't meeting the required quality for the injectant. So after various studies with the CSIR, as well as the University of Pretoria in South Africa, it was then decided to blend the water, to have a 1-to-3 ratio of reused drinking water to surface drinking water in order to meet the required water quality. To date, the recovered water quality has averaged about 610 milligrams per liter TDS and 1.1 milligrams per liter DOC. So to conclude, the Windhoek Managed Aquifer Recharge Scheme has achieved about 3,330 million liters that have been banked underground. It was able to environmentally and structurally protect the aquifer from further degradation, and also to refill the levels that had been previously overmined. It has been a more efficient storage compared to surface dams, where we have seen high evaporation losses. The losses are negligible for the aquifer recharge storage scheme. And then we have increased the water supply security during the droughts, where about 6 million cubes were abstracted per year during that drought season. Due to banking, we had the water reserves to actually supply the city of Windhoek. So it's been a key tool in implementing climate change adaptation strategies for the city, and to provide the residents of the city of Windhoek with a safe, clean drinking water supply during times of crisis. So I just want to share with everybody here more, if you to see more information, we have had recent reports on the aquifer recharge scheme, and including the reclamation plant, and you can go to our website. So I'd like to thank you all for your attention. Thank you so much.
Thank you so much, Berenice, and apologies for the interruption. We had a question actually on the acceptance of recycled water. How have citizens accepted recycled water in their taps?
So the first reclamation plant came online in 1968, and this was after a lot of research went into reclamation from the 1950s. So in 1963, it was decided because of the extreme drought, Windhoek had literally run out of water, that they would bring on the reclamation direct potable reuse for the citizens of Windhoek. But since then, there is some negative connotations that come with reuse water, and public acceptance is very important. So with the new plant coming online, it was decided to do various media campaigns, tours to inform and engage the general public, as well as educate them about the process and share with them the quality results that we have gotten over the last 50 years of reclaimed water. So it is very important to get public acceptance, because it can lead to decommissioning of various direct potable reuse facilities. So it is important to engage with your stakeholders and to educate the public about the process, and also about the safety in regards to direct potable reuse.
Thank you, Berenice, and probably also the positive terminology, you know, and making sure we use the right terms, I guess, in explaining. Yeah.
Yes.
Okay, I think what we'll do is, thank you, Berenice. We'll move on to the panel session, where basically questions can be asked to any of the speakers, and vice versa. Speakers can ask other speakers for some questions. And we actually had one here for Carrie from Sanitation on one of your videos, Carrie, on whether you can talk about the financial performance.
Oh, sure. Broad question. I will try and cover it off. So Sanitation as an organisation runs a not-for-profit and a for-profit arm because we look at the entire sanitation value chain. And so on the containment and collection side, we run a non-profit. But when it comes to the treatment and reuse, the circular economy side of the business, we are very much a for-profit business. What we do has to support itself, and not only support itself, but be profitable enough that it attracts investment, because we are looking at reasonably large infrastructure investment when you look at a facility of the size of what we have built in Nairobi. So the profit model that we work on, or the business model that we work on, is very much focused around how we extract maximum dollars per tonne of waste that comes in, and how do we minimise the costs of operation, so that we reach that sweet spot of a circular economy approach that does stand on its own 2 feet and can attract not just impact investment, but just straight commercial investment as well. So very general answer to the question about financials, but at a high level, that is what we are pitching towards, and that is the model that we use for expansion, so that we can talk to investors from the perspective of not just invest in this because it is the socially correct and right thing to do and will make a positive difference, but also because we can justify the investment and pay back that investment over time.
Great, thank you. And Berenice, you had a question you can ask Carrie directly if you like.
What happened?
Yeah, we can hear you. You want me to ask the question?
She may have frozen.
Yeah, so Berenice asked you a question on the waste characterization and separation of the compost. How do you do the waste characterization, separation of the compost at collection to get appropriate quality of the compost?
So we take on a number of sources of waste. We started with our own toilet network, which is container-based sanitation separated at source, which gave us the dry matter and the wet matter separate, which we then, as we expanded and built out, we brought on other types of organic waste from all of your normal sources, market waste, hotels, general commercial waste, where either we are working with the party to separate, or we manage the separation. We do not currently work directly with municipal solid waste. That is one of our R&D waste streams at the moment, to identify how we can effectively separate the organic fraction out of municipal solid waste, because that is a huge problem and pain point that needs to be solved. But at the moment, that is only in the pilot stage and smaller scale for us. It's not part of our lab scale solution. So on the separation side, Denise, that's effectively Synergy's responsibility to make sure we've got the right inputs coming into our processes. And on the characterization side, we've spent the last 10 years effectively building up a database of feedstock mixes that we can use, so that we can, harking back to that financial question, extract maximum dollars per tonne of the mixed waste that we bring in. So we're working out, what do we feed to the BSF larvae to maximise their growth? What do we put into the compost mix to maximise the nutritional profile of the fertiliser that we produce? What do we put into our briquettes to maximise the calorific value for the burning? So that characterisation piece of the various waste streams is really important as well.
Thank you, Carrie. I've had quite a lot of other questions that came through. There's a general one to all of the speakers. What are the current barriers for greater uptake? I don't know who wants to take that one. Barriers for further uptake? No takers?
Oh, well, I can try.
Karthik?
Yeah, sure. I mean, the most obvious one is the yuck factor associated with different end products. So I'll just talk beyond just water. When we talk about, let's say, fertilizers even coming from human waste, perhaps the perception is that we're just going to take the human waste and just apply it to support crop production, and that's really not the case. When we are talking about technologies, including those that Carrie presented and some of the ones I presented as well, there are barriers that do allow for a substantive or substantial reduction in terms of the target pathogens, while allowing for recovery of carbon and/or nitrogen and phosphorus. So I think maybe this is not mentioned enough, but that is happening, and so that's a barrier, and then perhaps ways by which these barriers are being overcome as well. One of the biggest barriers is actually not understanding or not recognizing what the market is in terms of the product, and it's ultimately then ending up making the wrong product, and then that has then cascading impacts back upstream as well. So that can be very dangerous.
Thank you, Karthik. Actually, there was a question for you as well, going back to your presentation, whether your concept has been demonstrated to date. Yeah, so yes, not all of the directions I mentioned, and that was really the point also of the presentation, to really open up new lines of discussion at least. But yes, I mean, even beyond methane, there has been significant activity. I can start with the carbon side. And it's the same example I presented. So using the influent organic carbon, and it's the same for us also. Understanding the speciation of the carbon, characterizing the carbon coming in is also very, very important in terms of the let's say the volatile fatty acids that are produced, and in many cases these are being used inside the boundary of, let's say, existing treatment plants to either mainly nitrogen and phosphorus removal. Not recovery, but the carbon can be used for recovery of phosphorus as well. And there are other examples which are far more exciting, where we are talking about not just VFA, but using the volatile fatty acids the VFA produced to channel them into materials, chemicals, and so on. So that's really been, that's happening. Not very widespread, but that's happening more and more. What is also quite exciting is that, if you think back a decade ago, the focus was on converting everything into biofuels, more and more biofuels, without understanding really what the market is, the size of the market, the needs, and so on and so forth. But now it's very interesting. Over the last even 5 years, what has been happening is that the biofuel industry is now looking to be supported
by the production of some of these other materials and products that we have discussed today. So again, these are the ones which are driving, if not at the very least supporting the other novel biofuels that we've been so accustomed to hearing. But now it's based on this foundation, which I think is really exciting and really nice to hear for us, actually.
Stephanie, you're muted.
You're muted. Yeah.
Sorry, there was a dog barking, so I muted myself. Enrique, there is a question for you from Paolo Ronco. I don't know if you can see it. There is a question, if different level standard of water quality have been used to feed different kind of crops as per the EU regulation. Enrique, you're muted as well.
I'm sorry
Thank
for
you.
this. Okay, Stephanie, I have already written a little reply regarding that the different doses and combinations of different water from groundwater and reclaimed water were combined in a small plot of lands so as to compare.
Great,
so
wonderful.
At the end, it was excellent, and I must admit and confess that sometimes we have overpassed the quality standard regulated, at least in Spain.
Great, thank you so much for replying. Thank you, Enrique.
Thank you.
There was a question for Kartik. Kartik, is the lack of regulation to ensure safety for land applications also a challenge that needs to be overcome for reuse of treated waste?
Yeah, so especially when we talk about recovery of resources or even reuse of sludge, yes, absolutely. The last thing that we need to be doing is spreading pathogens and really compromising human health. And we don't want to do recovery for the sake of recovery, which is why some of the anaerobic processes, maybe I can present this slightly differently. Some of the anaerobic technologies that I presented very, very briefly, they do allow us to meet multiple objectives, and the first and foremost being pathogen stabilization. And in fact, if you look at the biosolids regulations in North America, even the operating retention times for digesters, anaerobic digesters, are solely based on not biogas production, but on pathogen reduction. And by the way, we just happen to produce a lot of biogas while doing so. And so yes, we need these policies. We actually need these regulations. And in parallel, if we can recover resources, that's all the better.
Okay. Thank you, Kartik. I think we're pretty much at the end of the session, so I'll pass over to my co-chair, Jay, who's going to do the closing remarks.
Thank you, and thank you for the presenters for setting the scene. I mean, this was a very important session, to unpack this value of wastewater. But, the presentations are so diverse that maybe we need to start changing the terminology rather than talking about wastewater, talk about the value of sanitation in general. Okay, because what we've seen is that, over the last few years, we're traversing beyond the boundaries of just treated effluent and reuse. From the case studies, we're beginning to see a whole world opening up on valorization and application, and Kartik sort of gave us an insight into the potential of, harvesting a lot of value-based products from human waste. Similarly, we have applications happening at, Sanergy, where we are also using very simple but sophisticated innovation in also tackling and opening up that circular pathway of managing human waste into the future, as well as the directions we're taking, that we can create this opportunity for direct and indirect reuse from a variety of mechanisms like aquifer recharge, other applications happening through the case studies we have seen. What is important is that I think we're at the pivot of this opportunity, where we're starting to demonstrate collectively the value of what we call wastewater sanitation to the future security, of people on this planet and the potential it has in the innovation we can apply to achieve that. So I want to thank everyone for actually opening up our mind and direction that, the next 2 or 3 sessions, we would be comfortably talking about black soldier flies, because they are a sophisticated machine, as well as, all the advanced membrane systems that also, put the kind of barriers we require to make this realizable going into the future. So thank you all that have opened up this pathway and shared this wonderful knowledge. It's been a privilege, and I'm hoping that you'll have set the tone for the next 2 days and many, many other sessions that's going to talk about the potential value of wastewater, sanitation, and sludges into the future. Thank you very much, and thank you to my chair for ably hosting us today in this short session. Thank you.
Thank you all. Thank you. And there's a slide with the next 2 sessions on valuing wastewater for new solutions as well. Thank you all.
Thank you. Take care.